today the Indian Math Olympiad, that's gonna be just so good. Okay guys, so today I'm gonna be solving a 2014 Indian Mathematical Olympiad question number 2. So, let n be a natural number and show that the floor of n over 1 plus the floor of n over 2, and we're gonna be just summing stuff up to the floor of n over n plus the floor of the square root of n is even. So how are we supposed to do this problem? Well, you see, first of all, what the hell is the floor function? The floor function, so this guy right over here, takes some number, a real number, and brings it down to the closest integer that is smaller than the given number. And so if we had, for example, 3.14 as a given number, then the floor of 3.14 is going to be equal to 3, because 3 is the closest integer that is lower than 3.14. If we were to take a floor of an integer, well, then we just wouldn't change this integer at all. So the floor of 5 is just a 5, everything like this. It's lovely. So how are we supposed to solve this problem? Well, I would honestly just opt for using induction here. And why is it so? Well, we're dealing with natural numbers. We're dealing with natural numbers, summing those up, and if we will be able to get some kind of a connection between the floor of k plus 1 and the floor of k, then maybe we will be able to solve this problem using, well, induction. So let's try and do it. If we were to conduct a proof using induction, what's the first thing we have to do? Well, first of all, we have to prove that the base case holds. Well, okay, n is a natural number. Some people argue that natural numbers start with 0. However, I don't really care about the case of n being equal to 0 here, because I'm literally dividing n by n in this almost last floor right over there. So, well, 0 by 0 won't really make any sense. So I just say that our base case is going to be for n being equal to 1. For n equal to 1, what we're going to get? The floor of 1 over 1 is going to be the first thing, and then the floor of the square root of 1. Both of those are just nicely equal to 1, and so there's going to be equal to 1 plus 1, which is equal to 2. Well, 2 is an even number. Awesome. So now for the inductive assumption, what are we supposed to assume? Well, we're supposed to assume, for the second step, assume that there will be a k, assume that there will be a k, I'm not going to be writing that, such that k over 1 floor plus the floor of k over 2 plus a bunch of dots. I'm going to be summing stuff until we get to the floor of k over k, and then plus that lovely floor of the square root of k is even. And I would like to prove using the assumption that the statement, so this entire sum plus a square root, will be also even for k plus 1 being equal to n. So now for the third part, we would like to conduct the inductive step. Yeah, and I'm leaning back in my chair. It's quite hard for me to write things in a straight line, honestly. Okay, so now I would like to prove that the floor of k plus 1 all over 1 plus k plus 1 all over 2, and we're just gonna be summing stuff up until we get to, yeah, I can't be leaning in my chair when I'm writing, sorry guys, all the way up to k plus 1 over k plus 1 and a floor taken off of it, plus the floor of the square root of k plus 1. So the fundamental question we have to ask here is how to relate, I'm gonna even write it down honestly, so how to relate the floor of k by some, let's say, m, to the floor of k plus 1 by the same m. Well, I would like to actually answer this question using a kind of a piecewise function. So I'm gonna move this thing here to the left hand side of my board, and let's answer that with a piecewise function. So our floor of the k plus 1 divided by m is gonna be equal to, that's, let's say, a bracket of some sort, that's gonna be equal to the floor of k over m in the case where m does not divide k plus 1, yeah, because then it's just going to be rounded down to the same value it was rounded down before we increased the value of k by 1. And then we have the second case where the k is going to be equal to the floor of k over m plus a 1 in the case of m actually dividing k plus 1. Yeah, lovely. Okay, so we have that checked out, but there's still one more problem, because here we have this floor of the square root of k plus 1, and how the hell do we relate the square root of k plus 1, the floor of the square root of the k plus 1, to the floor of the square root of k? Well, once again, how? Okay, so how to relate floor of the square root of k to floor of the square root of k plus 1. Once again, let's do this one with a piecewise function. So the floor of the square root of k plus 1 is going to be, not an integer part, but this floor is going to be equal to, so it's going to be equal to the floor of the square root of k whenever k plus 1 is not a perfect square, and also is going to be equal to the floor of, actually it's going to be equal to the floor of the square root of k plus a 1 after closing the half bracket there, whenever k plus 1 will be a perfect square. And well, there is one more pretty useful thing to see here about k plus 1 being or not being a perfect square. You see, whenever a number is a perfect square, so whenever we have a perfect square, say a squared, then we see that it has an odd number of divisors. Odd number of divisors. Well, why is it so? Well, whenever I have a number, like a regular number, let's call that number maybe n for now, we get that whenever we have n, and there is, let's say, a d which divides n, d is for divisor, then another divisor of n will be n over d, because it will also divide n. Yeah, that's without a doubt. And the product of, what will be left after this kind of a division is going to be just d. And so we can just about go on and pair up regular, all the regular numbers, those divisors into pairs of divisors, let's say d1 and d2, such that the product is going to be equal to the number that they divide. The problem is that whenever we have, well, perfect squares, let's say a squared, then there will be this one special divisor, which will be the square root of a, which will definitely will divide a squared. However, the only thing that when a squared is multiplied by, when the square root of a is multiplied by, then it's going to be equal to a squared, is the square root of a itself. And well, we can't just count one divisor as two of them. It doesn't really make any sense. And so, as in normal, like regular numbers that are not perfect squares, so let's say, a squared, and I'm just gonna kind of, cancel it out, Then we have an even number of divisors. An even number of divisors. And so we can actually use it to help us solve this problem we've got right there. Why is that so? Because now, when we look at this case, once again, at this case of n being equal to k plus 1 in the inductive step. Well, let's say, for the first case, for example, for the first case in the inductive step, that a squared is, a squared. Let's say that k plus 1 is a perfect square. Yeah, so k plus 1 is equal to some a squared. Well, what does it mean? It means that k plus 1 has odd number number of divisors. What does it mean? Well, it means that there will be an odd amount of cases, an odd amount of instances where the floor of k plus 1 over m will be equal to the floor of k over m plus 1. Huh? You see what I'm getting at? And so let's say that we will have 2b plus 1. Yeah, let's say k plus 1 has 2 times b plus 1 divisors. Yeah, something like this. Then it means that this sum k plus 1 over 1 floor of it, then floor of k plus 1 over 2 floor of it. Then I'm going to be summing stuff up until we get to k plus 1 over k plus 1 and floor of it, and then plus this floor of the square root of k plus 1. This part here in pink is gonna increase by 2b plus 1. And why is it so? Because we know that whenever k plus 1 is nicely divided by some number, then by some number n, then the floor of k plus 1 over m is equal to the floor of k over m plus 1. So with respect to what we have, what we had here in the assumption, yeah, so what we had here in the assumption, this orange sum is going to be greater by 2b plus 1. Yeah, and so we can just kind of go on and say that this thing I underlined here in pink, we can go on and rewrite it as stuff from the inductive assumption, yeah, stuff from the assumption, which is just the floor of k over 1, you know, the floor of k over 2, stuff like this, until we get to the floor of k over k, yeah, and then we just add those 2b plus 1. However, then, now one more thing, we know that k plus 1 is a perfect square. It is a perfect square, and so if k plus 1 is a perfect square, then the floor of the square root of k plus 1 is equal to the floor of the square root of k plus a 1 right over here. And so we get that, now maybe I should have actually put this guy in orange. Yeah, that would have made more sense. It's going to be equal to the floor of the square root of k and then plus this 1, because k plus 1 was a perfect square. And what do we see here? We see that this yellow part, the sum of those yellow numbers, is even, and the sum of 2b plus 1 and plus 1 is 2b plus 2. It is also even, so we're just summing up two even numbers to get an even number. And so we see that this entire thing is 0 modulo 2, so this entire thing is actually nicely divisible by 2. And now let's go on to the second case. The second case is going to be where k plus 1 is not, when k plus 1 is not a perfect square. But if it's not a perfect square, just as we had before, we will rewrite this entire statement. And well, I'm not going to be writing that, I'm too lazy for that, so I'm just going to copy it, paste, okay. And now there are going to be there's going to be an even number of instances when this thing happens, where the floor of k plus 1 over m is equal to the floor of k over m plus 1. Why is it so? Because k plus 1 has an even number of divisors, and so we can go on and rewrite this entire sum as, well, exactly this. So what we had in the inductive assumption, plus double b, because we say that k plus 1 has double b divisors, okay. And now what about this plus square root of the floor of the square root of k plus 1? Well, that's gonna be the floor of the square root of k, because k plus 1 is the perfect square, so that's gonna be just the floor of the square root of k. But once again, we know one pretty nice thing: the stuff that I underline in pink right now the sum of those things is even, and we are adding an even number of 2 times b. So the sum of two even numbers just has to be even, and so it is also, this entire thing is also even. So we had two cases. In both of those cases, in our inductive step, our sum is actually even. And so, ladies and gentlemen, I think it's a beautiful, beautiful proof. So what did we do here? Oh, it shouldn't be here. Shit. What the hell? Okay, so what did we do here? Well, we proved it by induction. We checked the base case. We assumed that the sum of all of those, k by something floor up to the floor of the square root of k is even. Then we, well, actually related, we thought how to relate this floor of k over m to the floor of k plus 1 over m. We managed to, well, put up a piecewise function that would describe this relationship. We also managed to put up a piecewise function that would describe a relationship between the floor of the square root of k plus 1 and the floor of the square root of k. Then we notice that whenever k plus 1 is actually a perfect square, it has an odd number of divisors, and when it is not a perfect square, it has an odd number of divisors, an even number of divisors. And then, basing on what we achieved right over here about the number of divisors of k plus 1, we brought up two cases for our inductive step. In both of those, we managed to prove it, and so we proved the entire statement. So I really hope you guys enjoyed it, and see you in the next one. Bye.